Hello everyone. In the last video, we talked about DeepChem library. So what we talked about was we had these smile strings, right? And we featureized it using conv-mol featureizer and train test split using specified splitter, and then we made a model, graph convolution model. So in this video we'll talk about some other splitters. So again, I have uploaded the dataset. It is the same Google Colab notebook that I used last time. If you have not seen that video, I highly recommend you go back and watch that video before you move ahead. So again, apart from specified splitter, we specified in here we specified a range of indices, test indices from 513 to 642, and the next splitter is random train test split. I think everybody is familiar with this random train test split. What we do is we just randomly split the data set, and first we have instantiated it, the random splitter class, and then again we are gonna be train test split using dataset as an argument and fraction of the train set. So 0.80, that means we want 80% of our data set to be in the training set, and seed is for reproducibility. So let's run this. Again, since this is 80%, length of train would be 513, and let's just instantiate our model as well, graph convolution model. Tasks is 1, mode regression, dropout 0.2, fit the model. So we have successfully trained our model, and now it's time to get the predictions. Again, same code, model.predict test dataset to get test y values or test predicted values, and model.predict train dataset to get the train predicted values. So here, and again this is the same code, R2 score. First we will see using sklearns metrics, and here test R2 score, train R2 score is 0.74 and test is 0.63, and this is with the random split. And initially we used the specified split, and that gave us an R2 score of 0.96 and for training and test 0.86. And if you use the same different seed, you're gonna get a different result. So make sure you take care of that as well. So yeah, for the Pearson R2 score, the training score is 0.95 and test is 0.88. So in this way you can do a random split as well. The next one is scaffold split, and little bit about scaffold split. I'm right now in the tutorial book that's on the DeepChem website, and it says the splitters tries to address the this problem of splitting where many molecules are very similar to each other. So it identifies the scaffold that forms the core of each molecule and ensure that all molecules with the same scaffold are put in the same data set. So again, this is a little different, where similar molecules are put, similar molecule with same scaffold are put in the same data set, maybe in the train, and then the molecules with little different scaffold are put in the test or in the validation. So yeah, so let's do this scaffold split. Again, instantiate the scaffold splitter class and then save our train and test dataset by calling a train test split method, and our train fraction is 0.80. Fit the model again and get the metrics. So here test train R2 score is 0.78 and test R2 is 0.68, and I think this is these are quite similar. Till now only specified split has given us the best train test results, and this is for the Pearson R2 score. The next one is a molecular weight splitter, and it's another splitter, performs data split based on molecular weight. That's the only explanation that's available in the book. So yeah, let's see how this one performs. Again, similar, instantiate it and save our train test data set in these variables using by calling test train test split method. Train the model and then call the predictions. So this is little better here. Train score is 0.83 and test R2 score is 0.739, and these are the Pearson R2 score. Training is 0.97 and test is 0.89. Similarly, we have different other splitters: min max splitter, butina split, fingerprint, and let's see if we can find the explanation here. Butina splitter is tries to address the problem of similar molecule. It clusters them based on their molecular fingerprint so that one with similar fingerprint will tend to be in the same data set. Again, it puts the same molecules in a single same data set, and that is grouping is based on molecular fingerprint. So this is similar to scaffold, and that we use the molecular scaffold to group together the molecules. In this we are using fingerprint. So another one was fingerprint splitter, and this uses tanning-mato similarity, and I've talked about tanning-mato similarity in my RD kit videos. So tanning-mato similarity measures overlap between two sets. Secondly, between so it's based on ECPF for fingerprints, and then it identifies these tanning-mato similarity with the molecules, and then it groups together. And again, it it splits the data set so that molecules in each data set are as different as possible. So again, similar molecules are grouped together, put in train, and the different molecules are put in other data set, validation and train. So let's run all three of these and see how they perform in our model. So for min-max split, we have got an R2 score of 0.85 for training, and for test it's 0.83, so it's pretty good. For butina split, we have a train R2 score of 0.86 and test R2 score of 0.889, so this is pretty good as well. And let's check for fingerprints. Okay, I think I missed the training, so let's just train the model. Here we've got the train R2 score of 0.89, around 0.90, and test R2 score of 0.73. So we saw a little overfitting in this. So this is how you can split your data set in different ways. And these fingerprints, butina split, these are little stringent tests because they are little challenging, because you're putting similar molecules in one data set and then testing on quite different molecules. So it could be little challenging, and which splitter to use, that totally depends upon your problem. Maybe if you're publishing, you can screen all of these and put the results of all of these in your manuscript. So again, it depends upon the problem you're trying to solve. But yeah, these are the different ways you can split your data set. Okay, so now we are done with the splitters. Now what we can do is we can see different models, what other models are there. But if you remember from the last video, I told you it also depends upon what type of featurizer that you are using. So featurizer and the model must be compatible with each other. Yeah, so let's see what other models are available. Now here talk about the GAT model, and if we go to the documentation in model classes, this is the cheat sheet. And GAT model, it's a class, it can be used for classification and regression problem, and it uses mole graph convolution featurizer. If you remember, initially for the graph convolution model we use convolution or con mole featurizer, which is based on Keras. This is based on DGL and PyTorch. So what we are gonna do here is, when we loaded our data set, so this is our data frame, and when we load it we need to put the featurizer as mole graph convolution featurizer. So yeah, that's the only difference from the previous one, and rest all is same. So let's do that. So here we are getting an error, failed to featurize data point 113 and 131. So let's see what are these. So row number 9 is methane, so it is just the smile string is just carbon, so it is not able to featurize that. And if we look at the data point 113, that's ammonia, and for 131 that's hydrogen sulfide with smile string as. So I think it's better to just get rid of these, so that's what I'm gonna do here. Just drop these data points 9, 113 and 131, and make sure you reset the index after you have dropped these. So now let's run this again. Yeah, so now let's split our data set. So I'm just using random splitter, and then I'm using GAT model. Again, number of tasks is just one, since we are dealing with the regression problem. And then dropout 0.2, graph convolution layer 64. Again, these are hyperparameters, you can vary them. Dense layer size is 128, and number of epochs I'm gonna be using just 50, because it will take a long time for these type of models to train. So let's wait for it to finish training, and let's check our metrics. So just with 50 epochs we are getting pretty good train and test R2 score. So you can go ahead and increase the number of epochs. Just to save time, I am just keeping it low, and similarly you can check your Pearson R2 scores. Yeah, so this was all about the GAT model. And for DAG model, again, if we look at it, DAG model, it requires convolution molecular featurizer, so the same which we use for our graph convolution model. And yeah, so let's featurize it again with convolution mole featurizer, and then we need to put a drag transformer, and we need to use a transformer with maximum atoms equal to 50. So we need to specify that, otherwise it might show some error. Again, train test split random, and then we are using DAG model now, and all these parameters are in here. Number of tasks, mode, dropout, number of graph features, and number of outputs, layer sizes. So yeah, these are hyperparameters, you can play with them. Again, these type of models take a long time, so let's just keep it to little low. This is just for tutorial purpose, you can just go ahead and train for more epochs. So for training 30 epochs, it is taken as 4 minutes, so keep that in mind. If you train it for more epochs, it's gonna take more time. Let's check the metrics. So training is 0.88 and test is 0.78, and these are the Pearson R2 scores. And last but not the least, this is one of the most advanced graph model, which takes in mole graph convolution featurizer. And let's first featurize it and then split our data set, again random split. And I'm gonna be training it for, let's do it for 30 again. Yeah, and then we'll test our predictions. So now you can see just with 30 epochs, training for 30 epochs, it has given us train R2 score of 0.97 and test R2 score of 0.96. And if you just compare it with the DAG model, we are using the same seed for random splitting, seed number 9, and we are training for the same number of epochs. And if you compare the statistics, test is 0.78 here, and here test is 0.926. So attentive FP is definitely better here. Yeah. So one more thing that I want to talk about is, let's say you want to predict for some external molecules. So let me just grab few smiles. So let's say you want to test for this methyl cyclopentane and 2-bromopropane. So let's just copy these smiles here. So our external smiles are these two, and so we need to featureize it. Since we are gonna be testing on this attentive FP, which is our latest model, and what we are gonna do is featureize it using mole graph convolution featureizer, and then predict using model.predict. So external test scores are these are the test score 1.72 and minus 0.418, and if we compare it with the actual values, which is 1.59 for methyl cyclopentane, and here we have 1.72, pretty close. This is minus 0.48 and this is minus 0.418. So yeah, in this way you can predict for the external smiles. Yeah, that was it for today's video, and in the future videos I will talk more about the use of DeepChem in modeling our molecular data. Thank you for watching.